All right, beautiful. Okay, quick lesson with something that's not very fun. Oh, be quiet. It's not going to kill anybody, hopefully. Most of it is a pre-calc review dealing with trig. Now, nobody likes trig. I happen to, but that's okay. We're going to talk quickly about some pre-calc stuff and then give you a whole bunch of calc theorems. If you don't get them down in time, it's okay. They're all in the book. In fact, I include the page numbers in the slideshow. You can go back later and add them to what you're dealing with. Okay, so we're going to do inverse trig functions, differentiating inverse trig functions. So you know an inverse trig function as the function that undoes sine, cosine, tangent, secant, cosecant, and cotangent. But then we're going to take the derivatives of them. So we're going to talk about some pre-calc with the 6 inverse trig functions. We are going to differentiate those inverse trig functions. We're going to review some basic differentiation rules. So at this point in time, if I have everything under control correctly, we are done learning rules for differentiating. So I have a big honking list of all the things you already know. And then, of course, you should be able to list the presidents in descending height. Tallest president? Abraham Lincoln. Shortest president?
Madison.
You think so? I have no clue. I'm just BSing my way through this. I don't know. John Adams, maybe?
No, we would.
Oh.
Here's an answer from Wikipedia.org. Madison was the shortest.
Oh, John with the winner on a Wednesday morning. Very nice. Did you pull that out of your butt, or did you really know that?
Use my resources.
Did you pull that out of your butt, or did you really know that?
We learned it like 2 weeks ago in history.
How weird is that?
My teacher's got me.
He would enjoy that kind of stuff. Okay, so we talked about ad nauseum the idea that all functions have inverses, but not all inverses have functions. Sorry, not all inverses. Wait, now I'm screwing up my own thing. All functions have inverses, but not all of those inverses are functions. That's what I tried to say. Why are the inverse trig functions, or why are the trig functions not? Boy, you'd swear it's Monday. Why are the inverses of trig functions not also functions? Go.
Because they don't always increase or decrease.
Good. Fancy term for that?
Monotonic.
Good. Strictly monotonic. Which means it doesn't pass the horizontal line test. Which means it's not one-to-one, etc. If you think of something like the sine curve just keeps bouncing up and down and bouncing up and down. So it doesn't satisfy any of that stuff that we just mentioned. So what do? Well, it would be nice if we could just say, okay, fine, we're not going to deal with it. We're not going to play with it. Done. It doesn't work that way. What we're going to do is we're going to take parts of the trig functions to guarantee that it becomes always increasing or always decreasing. Strictly monotonic, is one-to-one, passes the horizontal line test. And you've done this in pre-calc. You just don't remember it. So this is a big, scary chart. First of all, I wanted to mention that you are probably used to seeing notation like this for inverse functions. Okay, so that would be an inverse trig function. However, our book likes to use arc sine, and that's a fairly common way to, they mean the exact same thing. Inverse sine is the same thing as arc sine. Okay. Now, what do you need off of this chart? This is really where we're going to focus most of our attention. Okay. And what is that? Well, what we're doing is we're taking a function that is not strictly monotonic, that is not one-to-one, that doesn't pass the horizontal line test, and we're saying, okay, we're going to chop off a whole bunch of this graph and just focus on certain parts. And if we just focus on certain parts, we will get something that becomes strictly monotonic, one-to-one, passes the horizontal line test, et cetera, et cetera. Okay. If you look at these combinations, you'll notice that every one of them has quadrant 1. And this is 2021, so this isn't memorization. Back in the old days, I would show you some tricks on how to memorize that. You're not going to do that. You're just going to write it down and reference it. But the thing that they have in common is they always include quadrant 1, and they always include another quadrant where the value is negative. So for instance, if we look at tangent, we're looking at tangent as being quadrant 1 and quadrant 4. Quadrant 1 will give you a positive value. Quadrant 2 will be a negative value. Cosine is quadrant 1 and quadrant 2. It's positive in quadrant 1, negative in quadrant 2. Okay, so we'll always have a positive value and a negative value. And again, I'm going to go quickly through this. I'm sorry if you don't pick it up, but like it says here, it's in the book on page 373 if you want to clean up your notes by the end of that. And I'm also recording the lesson so you can go back and do that too. Pause the video, copy things down. Okay? Okay, so that means things like this. What is the arc sine of, the arc cosine of 0? What is it asking? Well, when we first started, way back when in precalc, when you first started learning the unit circle, you took a different approach to that, and that is, here's a value on the unit circle. What's the cosine of pi over 4? Okay. What's the cosine of 3 pi over 4? What's the cosine of 5 pi over 6, et cetera, et cetera? Now we're going backwards. Where on the unit circle will the answer be 0? Not a rhetorical question, by the way. I'm looking for an answer.
Pi halves and 3 pi halves.
Say again?
Pi halves and 3 pi halves.
Good. Yeah. Which one?
Oh, just pi halves.
All right, so we go back to this then. And so, if you didn't hear her answer, she said pi over 2 or 3 pi over 2. And then there's a whole bunch. Then you could do 5 pi over 2, 7 pi over 2, all of those odd numbers pi over 2, but we want to restrict that. So we're dealing with cosine, so we look over here, and we're dealing with this, which would be from 0 to pi. Okay. What about, where is the tangent equal to the square root of 3? Now, one way to think of this would be, what is the arctangent of the square root of 3 over 2 over 1/2? Well, this seems kind of wonky. Why would I do that? Because you should be familiar with square root of 3 over 2 and 1/2 on a unit circle. Remember, tangent x over y or y over x? It is y over x, right. So we're looking for a spot on the unit circle where the y value is going to be the square root of 3 over 2, and the x value is going to be 1/2. That would be pi over 3. In other words, big y value, small x value. Now, what if it's not on the unit circle? Then you pick up your handy dandy calculator and you type it in. Make sure, in this class, 99.99% of the time you should be in radians mode. If you're not in radians mode, it will give you an answer and you will have an indication that that answer is wrong. You'll think everything is peachy keen and go on from there. But when you're in radians mode and you type the arc sine, which is second sine of 0.3, we get a value of
0.305.
perfect. Accurate to 3 decimal places because it is AP Calc. And I don't know why there's an extra decimal in there. I don't know. Fat fingers when I was typing. Okay. That should not be there. That's silly. Okay, good. Now I hate to admit it, but none of that is calculus. That's all pre-calculus. And then this is also pre-calculus. As we start finding trig functions that involve the function and the inverse, we start putting them together. We knew this already because of stuff we did with inverses. And you'll notice here down in the example, we're going to have to be careful now with the quadrant restrictions. It would seem like they would cancel each other out and it would just be 3 pi over 4. It's not. It's pi over 4. Why? Because we have quadrant restrictions from that earlier slide. Okay? So we have things like this. Okay? The sign of the arcsine of 1/2. Well, where's the arcsine of 1/2? That's going to guarantee that it's in the first quadrant because it's positive. And therefore, the sign of something in the first quadrant would be nice, and that does cancel out and become 1/2. That's an easy one. However, the second one, not so easy. Because that value of negative pi over 4 is not in one of the quadrants for cosine, we have to do it the hard way. Okay, and what's the hard way? Well, what's the cosine of negative pi over 4? Negative pi over 4 is in the fourth quadrant. Pi over 4 would be 1 over the square root of 2. What's the inverse cosine of 1 over the square root of 2? So now we no longer want to be in the fourth quadrant. We want to be in the first quadrant, which would put it back up at pi over 4. Okay, so let me stop for a second. Does everybody understand what I just did? Okay, no? Okay, this is in the fourth quadrant. The cosine isn't supposed to be in the fourth quadrant. The cosine is supposed to be in quadrants 1 and 2. So they're not going to cancel each other out. A common mistake is people see the inverse cosine of the cosine and just say, well, it's negative pi over 4. You have to grind this one out the old-fashioned way. So I solved this. Okay. Negative pi over 4 is the same thing as 7 pi over 4, if you want to go that way about it. And this is 1 over the square root of 2. Do you guys do 1 over the square root of 2 or the square root of 2 over 2? What were you taught?
Square root of 2.
Okay. Because somebody had a Jones for rationalizing denominators. That's the dumbest thing ever. Yes, sir.
So before you do any of these, you basically just have to check whether or not, or which quadrant it's in and see if it agrees.
Correct. If we're looking at something like this where we're in the quadrant like we're supposed to be, because that's quadrant 1, then we're fine. They cancel each other out. Life is grand. If they're not, then you got to do it the old-fashioned way. Okay, so then the question becomes, in this part of it, where on the unit circle does the cosine give us a value of 1 over the square root of 2 based on that quadrant restriction of quadrant 1 and quadrant 2? And that happens at pi over 4. Okay. And then the last one, what if it's not on the unit circle? 2/3 is not on the unit circle. And so how do I solve that problem? Plus I'm combining all of a sudden cosecant with cotangent and a whole bunch of mess. If it's not on the unit circle, this is where you go back to the stuff that I know you did last year, which was draw triangles. Okay, so there's my triangle. I have some angle theta. When I take the cotangent of that angle theta, I get 2/3. Okay, so that's adjacent over opposite. And this should start coming back to you. How do I find this? Pythagorean theorem. Square root of 13. Once I get that, okay, so this stuff in the parentheses comes from the gets the triangle. Once I have the triangle, I can do any one of the 6 trig functions. What's the cosecant of that angle? What's the sine of that angle? What's the cosine of that angle? Okay, so cosecant is the reciprocal of sine. So that would be hypotenuse over opposite. So it should be the square root of 13 over 3. Yes. Beautiful. Okay? Again, if it's not on the unit circle, draw a triangle. This is actually the more difficult part. The differential or the derivatives is pretty simple. Okay, so remembering the precalc stuff that you hated last year, or disliked, I should say, is the hard part. Then we get into the okay. One other example here. This pops up. So here, this is nice because we're working with numbers. What if you don't have numbers? This happens a lot in some of the word problems we're going to be doing in the future. Notice the numbers are changed into a variable. If you have a variable, then you just handle it as if it was a variable. So x is the same thing as x over 1. And you'll recall from trig then that that's the opposite over the hypotenuse. How long is this? Close. Square root of 1, whoops, square root of 1 minus x squared. Okay. X squared plus this thing that we're looking for squared equals 1 squared. Okay. And again, then we get back to the same scenario we had in the last picture. We know all three sides. We can find any information, any one of the trig functions for that particular angle theta. So cosine would be adjacent over hypotenuse, so it would be 1 over the square root of 1 minus x squared over 1. Okay. All right, now the derivatives. This is a much bigger deal before the pandemic hit. What do I mean by that? Well, everything we're doing now is open notes, so all you have to do is make sure you have your notes under control and be able to recognize what it is we're trying to do. Okay, so here's the chart. This is fairly intimidating, but it's doable. Okay. I'm going to leave this up here for a couple minutes. I'm just going to talk about it a little bit, and then we're going to go from there. 6 trig functions. 6 inverse trig functions. Identify what u is, plug and chug. Okay, and that seems like a much bigger generalization, but literally that's what you're going to do. And I have a couple examples that we'll go through quickly, very quickly, because I want to get to the quiz. And again, if you didn't get this chart, it's okay. It's in your book. Or you can come back and watch. I'll have the slideshow posted. I'll also have this video posted that you can look through. Okay? So I'm going to skip this. I know you're going to freak out because you're not going to get a copy down. That's okay. Let's just look at a couple examples. I'm doing an arc sine. That's the first thing I recognize. Okay? Then I ask myself, like it says in red, what is u? U in this case is 2x. That's the only hard part that you need to worry about. Arc sine, and there's u. Because then all I do is I go back to this slide and I say, okay, arc sine. I need u prime, and I plug into that puppy down below. U prime is 2. 1 minus 2x quantity squared. Make sure you understand the difference between these, please. Okay, and then plug and chug. That process repeats itself. Arc tangent. What is u? U is 3x. Go back to the previous slide, plug and chug. You get your answers. Etc., etc., etc. Don't make it more difficult than it has to be. Okay. And you'll notice that I did a lot of work in this example for C that I didn't really need to do. If you can get to here, I'm happy. We'll talk a little bit later about how to go to there and when you should go to there. But for now, just understanding and applying the theorem is what we're looking at. And then the last one, same thing. What is u? Plug and chug. Click, 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 click. Okay, this, 2 seconds. This is all 24 rules that we have for differentiation. We'll spend some time on Friday going over these. You know all these already. You just don't necessarily know them. For instance, number 6 seems like a train wreck. That is simply the power rule. Bring the exponent down, reduce it by 1. Okay, you've done a lot of these things ad nauseum. Okay, we're done. Questions? Zoomers? Beautiful. All right, so let me do this. Discard that. Stop recording.